This is the Junior Math Challenge from 2025. Super fun paper. Let's just get straight into it. 10% of 20 is 2, and half that is 1. So that will how we do that. We can add these numbers up to get 9999, and these to get 3333. And clearly 3 lots of that fit into that, so the answer is 3. Your homework before you do every math challenge is to learn the prime factorization of the year that you're taking the challenge in. This one was 3 to the 4 times 5 squared. And because of that, we can tell that 15 is a factor because there's a 3 times 5 in here. 25 is because there's a 5 times 5 in here. 45 is 3 times 3 times 5, and there's enough of those things as well. 75 is 3 times 5 times 5, and there's all that in there. That is 3 times 3 times 5 times 5, is it? Something like that? 9 times 25. And there's enough of those things in there as well. So all of those things are factors of that number. Yeah, this person ran this thing in this time. That's 1 minute and 39 seconds short of 60 hours. That's 60 seconds. 60 plus 39 is 99. And here, this is a square. When you cut a square in half like this, that makes this 45 degrees. But of course, if this is an equilateral triangle, then each interior angle is 60 degrees, which means this difference here must be 15. And we'll circle that answer as well. These people swim in a pool for every 4 lengths. This person does 3, this person did 36. So we'll do 36 divided by 3. It's like a ratio, right? 36 divided by 3 is 12, times by 4 is 48. So Sandra swims 48 lengths, which we then just need to times by 25. Easiest way to times by 25 is to times by 100 and then divide by 4, or vice versa. So divide by 4 is 12, times by 100 is 1200. What's the difference between the smallest 4-digit multiple of 3? Now, multiple of 3 need to add up, need to have a digit sum that's a multiple of 3. So 1000 doesn't, because that has a digit sum of 1. 1001 doesn't, but 1002 does, because they add up to 3, which is a multiple of 3. The largest 3-digit multiple of 4, now 1000 is a multiple of 4, because 100 is. So therefore 996 is the smallest, is the largest 3-digit one. And the difference between those is 6. 8.8 kilograms is 8,800 grams. Then we literally just divide by 100. I'm not sure what the point of that question was, but okay, at least we get a nice free mark. All 4 digits of 2-digit numbers are different. So, okay, we want to make the smallest digit sum of all these things, or the smallest sum of all these things. Now, that means we want the digit to be as small as possible. So, it probably seems sensible to pick the digits 0, 1, 2, 3. Now, we can't have 0 as the first digit because that doesn't make a 2-digit number, but we can use 2 and 23. Sorry, 10, 10 and 23. Or we could use 13 and 20. As long as we put the 1 and the 2 first to make the numbers as small as possible, the units digits aren't going to matter because when they add up, they're going to make the same thing anyway. So it's fine. So this one here, we can set up an equation if you're someone who's confident with equations. So we can say L for length equals 60 plus a third L, and then we can times everything by 3. Make sure you times everything by 3 if you're ever doing that strategy. And then, of course, take away 2L, divide by 2. Sorry, take away L, divide by 2, and you get 90. You can also just do trial and error, right? Like you can look at these answers and go, okay, well, if that's the length, let's find a third of that, which is 25. And is that 60 plus a third of it? No, because 60 plus 25 is 85, so this doesn't work. Whereas this, like a third of this, is 30, and 60 plus 30 is indeed its own length. So this one works, and you could have just done trial and error, which is good. Yeah, 3 consecutive 1-digit numbers are okay. So this lists the 1-digit numbers. They're these. I probably should have put 0 here, but who cares? Now, the only things that are cube here are 1 because it's 1 cubed and 8 because it's 2 cubed. So we're using some string of numbers around. It's either 1, 2, and 3 or 7, 8, 9, right? Or 6, 7, 8, I guess. But 7, 8, 9 look promising because that's prime, that's cube, that's square. So we'll go with that. And then what's the product of these? Well, 7 times 8 is 56, I think. So when you times that by 9, the only reasonable answer here is, because it's going to be about 500, 56 times 10, right? It's going to be 504 without actually bothering to calculate it properly. Yeah, so this is a square. There are 2 squares here. It's kind of confusing as to what's going on right away, but there's a square here and there's a square here. Now, each of those squares is height 10, width 10, because they're square, sorry, 12 and 12, because they're squares, which means if this is 12 here and this is 12 here, they add up to make 24. So there must be 3 centimeters of overlap to make it only add up to 21. And now we can just do 3 times 12 for 36, and that'll be our answer. We have a bunch of rectangles, height and widths. The first one is 10 and 13. Then we add 2 to the width, to the height, and 1 to the width of each one. So that goes 12, 14, and 14, 15. and 16, 16. Now that one's square because the width is the same as the height. So there's one of them. And then you notice as you go further along that the heights become too big and the widths are increasing too slowly to catch up with them ever again. So there's only one of them that does it. It will never happen again. You probably just want to memorize some of these results here. This is 27, 64, and 125. When you add them up, you get this. And again, you may have memorized that that's just 6 cubed. Or you can just work it out pretty quickly that it is by just trying 6 times 6 times 6. And you get it pretty much straight away. Yeah, so £8, 13 ounces, 16 ounces a pound. So the first thing I did was said, well, what's 8 times 16? Well, that's 8 times 8 times 2, right? 8 times 8 is 64, times 2 is 128. Add another 13, and we get that this person weighs 141 ounces, which is 28 approximately grams. So let's just do 141 times 28. And then we'll also divide by 1,000 at the end. I obviously can't be bothered to actually do this, so I'm going to do 140 times 30. 14 times 3 is 42, add a couple of zeros on, and then divide by 1,000, and it's about 4. And we'll go with that. Probably some intelligent ways of doing this. 40% of 60 is 24, because 10% is 6 times by 4, so we're doing 20% of 24, which is, 10% is 2.4, doubled is 4.8. So that's just going to be 4.8 there. This one here, 60% of 80 is, or 10% again is 8. So therefore 6 lots of that is 48. So we're doing 40% of 48. Now at this point I noticed that I could just say that 4.8 is equivalent to 10% of 48. And this is 40% of 48. Add them together, you get 50% of 48, which I know is 24. So absolutely didn't have to do that trick at the end, but I thought it was nice. How many triangles are there here? Well, there's clearly the big one, and there's the one inside of it. So yeah, then there's this one here on the top section, and then there's the smaller one on the top section. So we're at 4 now. And then there's these two middle ones. There's one here, so that's 5, and there's one here, so that's 6. And then there's the bottom ones, one here, so that's 7, and one inside it is 8. And I think that makes 8. A particular number has exactly 9 factors. Now, the first thing that immediately triggers in my head as soon as I see 9 factors, think about how factors work. Think about the factors of 20. 1 times 20, 2 times 10, 4 times 5. They come in pairs. Each one has to multiply by something else to make it, so they come in pairs. So how on earth do you get 9 factors when factors definitively come in pairs to multiply with something else to make the thing you're talking about? Well, it's if one number is repeated. In other words, if the number you're going for is square. For example, the number 4 has 3 factors, 1 times 4, and then 2 times 2. But you don't count the 2 twice, it just uses itself to make 4. So this number is definitely square. The only square numbers in this list are 36 and 144, so I've narrowed it down to those two. Now it has 9 and 12 as factors. Both of these have 9 and 12 factors. So we're just going to have to look at which number has 9 factors. So let's list out the factors of 36, and indeed there are 9 of them. So this must have more factors, which I couldn't be bothered to work out or write down. Because why would I? This is the only question on the entire challenge, number 19, that I just completely skipped because I couldn't be bothered with it and I didn't understand how I was supposed to do it. Until you literally just write out the things it's telling you, 4 P's, 3 Q's, 2 R's, and an S, and then this, and then just do it, and it becomes exceedingly obvious what the answer is as soon as you actually just try, right? You're trying to make your cards have a number and a letter on them that's different every single time. So if you put a 2 with this P, you cannot put a 2 with any of the other P's because then you make a card that's repeated. So you have to put a 2 with a Q and R and an S. Like it has to be separated out into all the different letters because otherwise you definitively get a repeat. You can actually already answer the question from this because notice there's only one S. It's currently grouped with a 2. So the only one you can't do is obviously therefore S4. So E is the answer now. We've already got it. But I mean, if you want to make the 4 set, you've got 3 4s and there are only 3 letters essentially left because there's no more S's to pair with. So a 4 has to go with each of the remaining letters. And then a 1, there's only 2 letters left, so that has to go with each of those. And then the 3 has to go with a P. In any case, S4 is definitely the one that's missing. But yeah, I thought it was kind of an interesting question in the end, actually. As soon as you see a thing like this, you just draw it. So PQRS, and then you put the information in. PR is 6. This is obviously not to scale. QS is 4. And R is 1 centimeter nearer to S than it is to Q. So we're looking for a distance that is 1 more here than it is here, and these two distances add to 4. I think that would be 2.5 and 1.5, right? This is 1 more than this, and they add to 4. Which means this distance here is 3.5 because they must add up to make 6, and the total distance, we didn't even need this, the total distance from P to S is just 6 plus 1.5, which is 7.5. So here we've got a ratio of, this corner is 1/3 of the way along this edge here, which means we may as well just call this distance here 1 and this distance here 2, because then this is a third the way along, because the whole side length is 3, right? And therefore this we can also call 2 centimeters and this 1 centimeter. And now we can literally just work with areas, right? So the area of the whole square is 3 times 3, because each length is 3, which is 9. And the area of each white rectangle is a half, because it's a triangle, times 2 times 1, which is 1. There are 4 of those, that makes area 4. Do 9, take away the 4 for the white triangles, is area 5. So this square is definitely area 5, which means the ratio of the area of the little square, the grey square, to the big square is 5 to 9, because those are just the areas that I have. So yeah, this question is kind of cool as well. It's about the fact that whole numbers can only do certain things. We have 31 toffees in total. If you imagine having one bag of this type of thing, you've got 4 toffees, which means you need 27 more. But no toffees can come from the last bag, so you need 27 toffees from these bags. But you can't get that, because these bags only give you multiples of 5. So we can't have one bag of the first thing. So let's try 2 bags. That gets us 8 toffees. This take away 8 is 23, which we still can't make. 3 bags of this makes 12 toffees. Take away from that is 19, still can't make. 4 bags of this make 16, take away that is 15, and we can then use 3 bags of these. So that seems like it will work. There are 12 bags in total. So far we have 7. So therefore there are 5 bags left. And now we can just do, to work out the number of fudges, we can do 4 times 1 plus 3 times 2 plus 3 times 5, and we'll end up with our answer of 25. So yeah, again, this question is also leveraging the fact that whole numbers can only do certain things. It says that the distance from P to R via Q is twice as long as going direct. So this thing here is twice as long as this thing here. So if I call this thing here x, then this thing here is 2x, except this distance here is a whole number of kilometers. So the total distance all the way around is 3x, obviously. But because x is a whole number, that means 3 times x is a multiple of 3. So the whole distance around the entire thing has got to be a multiple of 3. And then you use the other information, which says exactly the same thing, just about this route from P to Q via R, and this route, and it says it's 3 times longer. But this is also a whole number of kilometers because of this sentence here, which means this is, the whole distance is 4y, but y is a whole number, so the whole distance is a multiple of 4. So the entire distance around, which is what it's talking about from P to P via the other 2, which is just the whole distance around the entire thing, is a multiple of 3 from this picture and a multiple of 4 from this one. The only answer here that's a multiple of 3 and 4 is this one here, because this one adds a digit sum up to 9, which is a multiple of 3, and 100 is a multiple of 4, so 108 is. So this will be our answer. 180 is divided by something with a remainder 5. That means that the last multiple that whatever you divide it by could hit is 175, because then that gives you a remainder of 5. If you got to 175, like if you imagine doing 180 divided by 175, the remainder is clearly 5, because the last multiple of 175 is 175. So all this question is asking us is how many multiples of 175 are there? Like how many numbers can get to 175 and therefore leave a remainder of 5 to get to 180, except for the exception that you can't use 1, because of course 1 totally gets to 175, but then it gets to 176, 7, 8, 9, and 180, and its remainder 0. And you also can't use 5, because 5 would then go to 180 and leave remainder 0 as well. So we're essentially just looking at for factors of 175 bigger than 5. And now the easiest way to find factors is to think about prime factorizations. So I did a quick factor tree and got this, and now we're just looking for what numbers we can make out of these factors, a bit like we were in question 3. So 25 is clearly a number we can make, because 5 times 5 is 25. 35 is a number we can make because of 5 times 7. We can multiply them all together and get 175, as we said before. But we can also make 7, right? Just using 7 on its own. So I think there are 4 ways of doing that. And in this cube, we want to make equilateral triangles. Now, the first step is just to try and make one equilateral triangle. If you go across the top row, that's one diagonal in length. And then you can go along this diagonal, which is clearly the same length, and this diagonal. So that's definitely an equilateral triangle, because each side length is just a diagonal of the square. Now you can keep this pretty much the same and just move this corner down to the opposite corner over there, and you'll make a second triangle. So that's 2 that we found so far. But you could also do the exact same, but instead of going across this diagonal, you could go across this one, and then you get another 2. So we're up to 4 as our answer so far. And now So the way that we'll get to 8 is we can do the exact same thing, except we can start our triangle on the base of the cube instead of the top. And then we'll get another 4, exactly like we did before, to give us 8 in total. Now, the reason that we can't then start making our triangle along each side of the cube, which is what you'd do if you ended up with 24, is because we've actually already counted those triangles via the ones we already made. Look, this triangle already has this diagonal here. Whereas the only triangles you don't make when you start with your diagonal on the top is you don't make any with diagonals along the bottom. So that's why we had to create those ones as well. And we end up with 8 in total as our answer. Really fun paper. Thanks for watching.